Welcome. Pharmacy regular students, welcome for genetics revision on population genetics. Hi. Jenny. Hi. I can see you, the first one. Hi. I'm with pharmacy today, pharmacy regular. We need to revise for Cat 2. So we are doing population genetics, but you can stay on board. Cindy, hello. Yeah, Cindy, yesterday I couldn't do it. I had a very strong cold, which was even going with my voice. So today I feel better. Yeah, I had a cold and yeah, it's gone. I had to take a bit of some hot water and ginger. Yeah, normal human being, you have to fall sick at some point. Thank you so much. Today I'm better. So when I thought about my students having a cut on Thursday, and I don't want to do it in the weekday because I need to give you time. Thank you, everyone. Thank you. So today, at least I have my voice. This voice, if you don't have it, you feel like you are just a shell. So today, we'll be able to be audible, I think. So I don't want us to take much time. Daniel Joro, we are still welcoming the students. Just log in, tell them to log into the channel. We can revise population genetics, my BpharmReg regular students, or if anybody feel that they also have to say hi, we'll be there to say hi. But today we are with regular BpharmReg. Then I'll have my upgrading BMLS sometime later in the week. But today I have my BpharmReg day. Kindly, I need to see Steve. I've seen Cindy. I need to see Steve. Yeah, thank you so much, Jenny. You already on your holidays. You already went back home. So you also enjoy your holiday. All the exams were done and you started your holiday. All the best with your holiday, Jenny. Yeah. So I'm waiting for Steve as the other members log in. I've seen Cindy. And then we can start and then we'll join. When the others are joining, we'll be able to continue. Then they'll keep on joining, because if you wait for them to come on board, we can wait for a longer time while others are coming in slowly. So we don't want that slow logging in. Huh? We just come on at once, then we can do it for 1 hour, then we go. Yeah. So I'm waiting for Steve. Keep. Cindy already there. So Cindy and Kip will tell me to start, because I always ask for permission from the class rep and the deputy class reps. We have to start when they're there. So I sent the revision questions. The revision questions, when you look at it, it was written in BCHB. It doesn't mean that things are different, because the pharmacy students are like doctors, just as doctors also are doctors. The pharmacy students are like doctors. So the content is not different. But now the bit of the Mendelian genetics we already covered. So we're just going to start on the Hardy Wayback. I just forwarded the same thing because it's the same copy which I used for MBCHP. So we're going to start with the Hardy Wayback. Is Steve there? Cindy, you can tell me to start. But I need the students to participate, because we are going to calculate. And then they are the ones who are going to tell me the values there on the chart. Huh? We are going to calculate. So wherever they are, we need to be active, my students. As we calculate in class, we are going to calculate, sorry. I'm going to show on the board, my small board, how we are going to do it. It's my network. Or is it hanging for you all? Can you answer Natasha Hassan? Natasha's network is having a problem. Yes, we can start. The rest can join. And the ones who are, yeah, we are at 30, they continue joining. So I thank you all for always coming on board. And you always have the live sessions for revision. And for your likes, you always like, you comment. You are free to do anything, as long as you don't use abusive languages, because here we are learning. So you can share your ideas, what you think, and I'll always be able to answer in relation to whatever we are doing. You can like, you can keep on subscribing. You can also share with the other students. It doesn't mean that it's only for the MKU students. It can also help the students from other universities if they want to. So what I'm saying, my students, we are going to calculate. So I'm going to get the answers from the charts. I'm just going to explain whatever we are going to do, calculate, and then we find the genotypic frequencies. Somebody tell me in the chat, and that is the answer I'm going to write so that we agree. That's how we are going to understand, so that when the cut comes on Thursday, and then the main exam as well, we'll be able to understand what we are doing. So I've already gotten permission. Will be posted on the channel for later review. Okay. So I'm already saying that we are starting. Cindy already gave me an okay. I didn't see Steve, but I know he's there somewhere. We are starting with the Hardy-Weinberg. I separated them into calculating the heterozygous, Hardy-Weinberg assumption, multi-allelic, inbreeding coefficient, and lastly, the chi-squared of fitness test. So let's start with the calculation of heterozygous. If I don't touch all, I might touch the first, how many? The first 6, for example. And then the other students can say, which one else can we do? Or we can also do all of them. Me, I'm fine, so that the students can get it well. It can well enter. We are talking at question number 1. I have to print it out so that I can see. Ability to test PTC. I think it's phenyl thiocarbide. This is always the experiments which are done in the lab, the practicals. If there were for one for genetics, you want to see if other students can test or other students who cannot test. But nowadays, there are no practicals in genetics in the labs. So these are a bit of the small practicals which are being carried out in the lab. But let's go back to question number 1, calculating heterozygous. Ability to test PTC is due to a single dominant gene allele, capital T. Now I tell you to use letter T, and somebody comes with their own letters, surely. If you come with your own letter, and I've told you to use that letter T, I'm now talking about the Mendelian. Here we are not going to mind much about the capital T. What we are trying to look at, that capital T stands for P, and then the small t will stand for Q. But then in the other case of the Mendelian, don't use your own letter. Please use the letter which is given. Even if you see it in exam, use the letter which is given. Don't use your own, because I'll minus some marks there for not heeding to the instructions. So we are saying for somebody to test Faith, hi, for somebody to test this chemical PTC is the dominant allele T. So those are the people who are capable of testing. What do they say? You sample 215 individuals. It means the N is 215. The total number of people in that population are 215. And then they're determined, you sample 215 individuals and determine that 138 could detect the beta test of PTC. So we are talking about P already taking the 138. But we said that we are interested in the people who cannot taste. We are not interested in the ones who can taste. We are looking for Q squared. We are interested, those people who can taste are normal. They don't have any problem. But these people who have the problem with their sense of tasting, is there in English like that? Their problem with the sense of tasting. Those are the ones we are looking for. So they are saying 138 can taste. If you remove or if you minus 138 from 215, you'll remain with 77 to be precise. So we are looking at the 77. So when you're looking at the 77, we mentioned that Q squared is equivalent to 77 over 300 and what? And 15. We start from there. I just put a line that so that I can know that I don't go up on that line, because if I go up, the students will not see. So I had put a line where I can know. I start writing from that line. So the Q squared, the ones who could not test, are 77 over the total number of people in the population, 315. That is Q squared. So we need Q. Let's start calculating kindly. We need Q. So Q, you will do square root of whatever you get after dividing 77 over what? Over 315. Divide 77 over 315. Oh, good. Amos has already given us. And we have to agree. Amos has said it is 0. Amos, you tell us Q is 0.358. Do you agree? The other ones, we have to agree. Amos has already given us the calculation. Do you agree? Another person, we want to agree with Amos because I'm going to write on the board 77 over 315. Is it 315 or 215? Oh, sorry. Sorry. Thank you for the correction. Yeah? Amos, calculate again. Sorry. Good. 0.598. 0.598. Amos, I hope you used 215. Sorry for that. I want us to agree. Good. Phoebe has confirmed. Thank you. Now, the rule says allele frequencies. Hadi Weinberg law says the allele frequencies should add to 1. So the easiest way to find P is what? 1 minus 0.598. Can we find P? We are looking at allele frequencies. We already have our Q. It means P is what? 0.402. Somebody? In the charts, I'll be able to write whatever you give me. Correct. Natasha says 0.402. Those are allele frequencies. Let's go back to the question. So, sorry. Thank you so much. Yeah, everyone agrees. So in calculating the heterozygous, you have to start with the Q squared. You are looking at that rare allele, which makes this population not to test. The ones who can test are fine. We are looking at the ones where there is a problem. So you do Q squared. The Q squared get the square root, we get the Q. So at first, you start by looking at the allele frequencies. You know, in the other ones, there are places where we start with the genotypic frequencies in order to get to allele frequencies. But here we are starting with allele frequencies. And let's go back to the equation. So the equation says, calculate the allele frequencies for each allele. Si unaona vile ni rahisi. Just say Q, clearly show Q 0.598, P 0.402, that is agreed. And then they are saying, calculate the allele frequencies of each allele and the expected genotypic frequencies. Genotypic frequencies give us P squared. Somebody give us 2PQ. Somebody give us Q squared. Then we are going to multiply by the total number of people in that population. First person, just say P squared is this. And then you are going to multiply by 215. You multiply by the total number of people in that population. Let's start with P squared. Remember, our P is 0.402. Our Q is 0.598. Can you do 0.402 squared? Then we do 2 times 0.598 times 0.402. Ah, good. 0.162. Thank you. The second one, 2PQ. Remember, even all those should add to 1. Allele frequencies, genotypic frequencies should add to 1. And then the expected genotypic frequencies should add to 215. So that is the law. 0.481. Thank you. The last one, Q squared. I think we already have it. Is it? It's what? Oh, before they find the square root. Just do Q squared. You tell us. Can somebody help Natasha? Oh, Phoebe already gave us Q squared 0.357. 0.357. Let's see if it adds to 1. To be sure, 0, 14, 19, 22. Yeah, correct. Now, those are genotypic frequencies. They are not expected. So from whatever we get, can somebody give us the total for P squared, for 2PQ? So whatever the value you got for P squared, can we multiply the 215? Give us the total number, the total value, sorry, P squared. So multiply with 215. The 2PQ multiply with 215 because they ask the expected genotypic frequencies. Expected. 0.162 times 215. Hi. Phoebe, Natasha, Harold. Can we calculate the expected? So whatever we got from the P squared to PQ, 34.83, is it the first one? Just tell me for P squared. I'll know it's genotypic frequencies. Natasha, is it the first one? Just tell me P squared 34.83 to PQ. Because I want you people to calculate 34.82. Thank you. And then I saw 2PQ 103.42. Harold has given us 103.42. Then Q squared, somebody? Yeah. Thank you. Q squared, I'm waiting for Q squared. Oh, did somebody give us? No, it can't be 0.357. We are multiplying with 215, the 0.3. Talha, 76.75. That is the last one, 76.75. Yeah. When we add, it should come to 215. That's already what? 9, 12, 9, 1, 14. Yeah. That is 215, 214.99. So you are exact. 76.76, correct. If it comes 76.76, it's exactly getting us to 215. So the expected genotypic frequencies for P squared homozygous dominant is 34.82. For 2PQ is 103.42. For Q squared is 76.76. If you bring 76.76, it will bring it to 215. It has to add up because that is the law of Hardy-Weinberg. Easy. Question number 2. We are still under heterozygous. We are going to have several examples so that, sorry, when the cut comes, you have to get it right. In 9%, we are at question number 2. We are only working on Hardy-Weinberg population genetics. If 9% of African population is born with a severe form of sickle cell anemia, what percentage of the population will be more resistant to malaria because they are heterozygous for sickle cell gene? So you already know that sickle cell anemia is autosomal recessive disorder. So you know the 9% has been assigned to Q squared. So Q squared, you'll be able to see the video. It will save itself when you go to the channel. You can revise even tomorrow. So they are saying Q squared is 9 over 100. And this one I think is easier. It means Q squared, you look at the square root of 0.09. Q will be 0.3. Am I right? See, the square root of that one is 0.3. We have to agree. At that point, do we agree? Correct. Natasha says, yeah, in short. It means our P is 0.7. And we learned about the model, the selection model. Even Nondia agrees, Mohammed agrees, Solange agrees, Blessing agrees. That's fine. It's good to move together. We agreed in the selection model, which was more like the stabilizing selection, we can round off to what? Why are you rounding off? Daniel, which number are you in? We already number 2. What are you rounding off there? I don't like rounding off because it makes some values to be lost. I always like, if it's something obvious, like 1 decimal point is fine. But if it takes us to 3 decimal points, it reserves the value. Because if it's 3 decimal points and then you try to make it to 2, or possibly if it's 2 and 3, you make it to 1 decimal, you lose a lot of value. But I always look at how the student understood the assignment and how the student reasons and get to the figures. As much as in mathematics, you talk about plus or minus 1, sometimes it doesn't apply too much. You know, the answer can be 0.03 or 0.04. That is the exact answer. You'll find some students with 0.05. You'll find some students with 0.03. You'll find some students with even 0.06. They're close to the answer, depending on how they go. But they can't get the exact marks at the ones who got it right at 0.04. So sometimes rounding off do not help. But in this case, it's obvious, it's 0.3. So you'll get at 0.7 as the dominant allele. Now, I was on to that model, which explains much about the sickle cell anemia, having known that it is autosomal recessive disorder, as we did much in Mendelian genetics. So you get a point where we are talking about stabilizing selection type, but the selection model will always be selecting against homozygous dominant and homozygous recessive. Then it selects for heterozygous. So we are being asked the number of the people who are going to survive. They won't die of malaria, they won't die of sickle cell. So you are told to calculate. Okay, it was for number 1. Okay. I don't know where we are supposed to find square root of the allele first. But that is what we are doing now. So where do you want to find the square root? Delphine, can you concentrate? Put your mind wherever we are. And that's why I've separated calculating heterozygous. I've separated inbreeding. I've separated chi-square test so that you don't go around square rooting everything. There are questions where there is no square rooting. So for now, we are square rooting because we have q squared. We need q. So we need to find the square root so that we can get to q. So don't mix things up, Delphine. That's why I didn't mix them up. I separated the equations where square root is needed, the equations where we are not going to square root. You get? So at this point, we are square rooting. But what are we dealing with now? We are working on heterozygous. And in which cases? Most of these cases will always work with autosomal recessive disorders. Or you find a situation where other people can taste, other people cannot taste. Other people can smell, the other ones cannot smell. We are interested in the people who cannot taste, the people who cannot smell, the ones who failed, the ones who passed. We don't mind about them. Yeah? How do you tell between observed and expected genotypic frequencies? Grasha, you are in class? Yeah? Were you in class that day when we were working? In fact, most of these expected and observed, we did them in lecture 8. You saw when we were looking at inbreeding, we are going to need the expected. So the observed are the raw data. You see, the genotypes for the raw data. Somebody gives you about the genotypic frequencies for all those. They are talking about the genotypes for homozygous dominant. The one which you get at the statement, the first time, that raw data, that is observed. Expected, you know, the genotypes which exist, which we talked much about, are always 3. We either have homozygous dominant, heterozygous, or homozygous recessive. So we have p squared. P squared stands for homozygous dominant. You will get the frequency. After calculating the allele frequencies, and you know each of the allele represents which value, then you will be able to substitute them with the p squared, q squared, and 2pq. Then you multiply the total number of people in that population. At that point, you are calculating expected what? Genotypic frequencies. Grasha will be able to understand as we proceed. So just pay attention where you feel you don't understand. I'll be able to highlight. But you're going to understand them well when we go to inbreeding and the chi-squared fitness test. But what you have to know, the genotypes which you are given in the raw data, those are observed. For you to calculate the expected, you have to start by calculating the allele frequencies. Then out of the allele frequencies, you are going to substitute p squared, which stands for homozygous dominant, 2pq, which stands for heterozygous, q squared, which stands for homozygous recessive. Then you multiply each one of them with the total number of people in that population. You get? You're going to understand that. So we were still at this point. We were talking about this model. Oh, good. Thank you. This model which talks about selection for heterozygous. So the statement asks, what percentage of the population, and if I talk about percentage, please give me percentage. If I talk about number, please give me the number. Don't twist my mouth what I did not ask. I tell you to give me the percentage, and then you are giving me the number. No, they are two different things. So they are talking about what percentage of the population will be more resistant to malaria because of why? They are heterozygous. It means 2PQ times the total number of people in the population, they are 100. So even if you want to know the number of people, or you want to know the percentage has to be 100. But still, the total number of people here are also 100. If they want percentage, we'll multiply by 100. So 2 times P was 0.7, Q was 0.3 times 100. It means 2 times 0.21 times 100. It means 0.42 times 100. So 42% of the population is heterozygous. Yeah? Is it right for the ones who are calculating? If it's a bit direct, then I can also calculate. Only the cases where I need to confirm from your end in the calculation. We are at number 3. We can do all of them so that it sticks. Yeah? Very good. 42%. Thank you. So, question number 3. We are trying to understand at what point, if you're asked, try to imagine we can square root, we don't square root, you do expected, you do without the square rooting, you have the multi-allelic, you know what to do. So that's what we are trying to put so that we can understand it clearly. Whenever it comes to exam or it comes to cut, you know what you're doing. Allele T, I think this one is similar. I'll skip it because it's similar to the first one. It's only that here we are talking about 58 of the non-testers. Yeah? Oh, Steve, you are there. Welcome. Question number 3, I'm going to skip it so that you can go to 4. You can see it's the same as 1, but you're going to do the non-testers, which are 58, over the total number of 500 students in that institution. 58 could not test. The other ones, 442, who could test. We don't mind about them. They are fine. We mind about the 58, the non-testers. And then you are going to do 2PQ to find the number of students. You'll multiply by, yeah. So it's the same. So allow me to skip number 3. You can do it on your own. 58 over 500, that is Q squared, do Q, the way we did 1. Let me go to 4, if you won't mind. Within a population of butterflies, the color brown is dominant over color B for white. Remember, in this Hardy Weinberg, don't do me a Punnett square. I'm not going to give you any mark on the Punnett square. Here we are calculating the genotypic and allele frequencies. The Punnett square apply to Mendelian genetics, Mendelian disorders. And that's why here, I don't even ask anything concerning the alleles and the genotypic frequencies. So, don't give me the Punnett square. Just go straight and do the Q squared, or you go straight to the genotypic frequencies the way the statement goes, and we are there to calculate. So here, no stories. But the Punnett square helps much in multi-allelic so that you can know which one of these is allele frequencies, which one of these are genotypic frequencies. We are going to learn about that. So we are talking about a population of butterflies, color brown, dominant over color white. It just guides us to know that Q squared is the recessive allele. And now we know which one of these is recessive. If 81% of all butterflies are white, remember, the dominant is brown. The white one is recessive. Calculate the percentage of butterflies in the population that are heterozygous and the frequencies of homozygous dominant, not individuals, but butterflies. Butterflies cannot be individuals. Those are insects. So we are talking about Q squared. They've said the white ones, which are recessive, are 81%. So Q, we are going to do square root of 0.81. Q will bring us to 0.9, right? Meaning P is 0.1. 2PQ equals to 2 times 0.9 times 0.1. Will it bring us to 0.18? Just confirm for me if what I'm doing is right. And they're asking what? Calculate the percentage of butterflies in the population that are heterozygous, 18%. Another question asked on the same, that frequencies of homozygous dominant individuals, P squared. What do you do with P squared? It is 0.1 squared times what? 100. Can somebody do for me that one? 0.1 squared is what? Is it 0.01? It means 0.18, correct? 0.18. 2PQ is the 0.1. Good. Steve says yes. So the heterozygous are 18%. But we've been told to get the individuals who are homozygous dominant. Remember the P is 0.1. Do 0.1 squared times 100. I think it's 1%. Phoebe, Natasha, Kip, or even Ntwari, Innocent. 0.1% squared is what? It is 0.01. Because a number times 1 is 1. I'm waiting for that answer. Is it 1%? Good. Thank you. P squared, 1. They are asking about the individuals, not percentage. Did they ask about percentage? Because we total we have, so it is 1. Is it 1 or 10? They don't want 1%. They want the number of individuals. Remember, they are 100. Frequency. Genotypic frequency. Is it still asking for percentage? No. Genotypic frequencies. So if you talk about the frequencies, for P squared, for it to form the individuals in that 0.1. If you do 0.1 squared, it will give you the frequency. And then the individuals will multiply by 100. So the frequency is 0.01. 0.01. The frequency, genotypic frequency, that is what they're asking, not the 1%. The 1% will come in percentage. But this 0.01, if you multiply with 100 persons in that population, it means P will come to what? Are you getting? Yes. That is the frequency. They're asking for genotypic frequency. If you're asked about the genotypic frequency, 2PQ will remain like this, Q squared will remain like this. So you substitute with the frequencies which you already have, the allele frequencies. So they're talking about, or we don't know how to read. Calculate the percentage of butterflies that are heterozygous. That one we've done. Now here in homozygous, frequency of homozygous dominant individuals. frequency of homozygous dominant. Homozygous dominant is the genotypic frequency. And the genotypic frequency, it means the genotypes we have are p squared, 2pq, and q squared. So you have to get p squared, meaning p is 0.1 times 0.1. So the genotypic frequency for p squared, good, that is the point, 0.01. Correct. Can we move to question number 5? Or somebody still feels something is not clear? Oh yeah, even Tuari said up there, Nodia said down here. In humans, we are at question number 5. We are talking about the rhesus factor. The story is a bit long, but we are going to shorten it. The rhesus factor, we are in question number 5. We are still talking about heterozygous, kindly. We are on heterozygous. So that when we move to another subtopic, Obize, don't just say no. Tell us where you don't understand. Obize Junior, tell us what you don't understand. Yes, one person. Kipkoech is talking about the number of individuals. But then, if you talk about genotypic frequencies, Obize, can you tell us why you have the no? Or you are not even one of us? We are reading question 5. As you tell us why you don't get or what you don't get, we'll be able to clarify until we move together. The rhesus factor, genetic information is inherited from our parents. How did we get the number of frequency? Obize, why are you in my class from the start? I want you to differentiate allele and genotypic frequency. Can somebody answer Obize as I read question number 5? Obize, but you have to tell us what you don't get. Can you differentiate the allele and the genotypic frequencies? You know, we only have 3 genotypes. Yes, if you can differentiate. If you talk about the genotypes, there are only 3. Homozygous dominant, homozygous recessive, and heterozygous. It means it brings us in the biallelic system where we have 2 alleles. We've already learned about the biallelic when we were starting our genetics class. You either have the dominant and the recessive allele. You get it. So if you look at, that is why we started with the subtopics, the calculating heterozygous. We are starting, this is bottom up. Is it bottom up? Because in the cases where we are introducing the genotypic frequencies first, we are starting with up bottom. So this one, you start with getting the allele frequencies first. After getting each of the alleles, it is easy to substitute when you want p squared, when you want 2pq, when you have, when you have 2pq, q squared, and p squared. Those are genotypic frequencies. And here, it straight tells us that it needs frequency for the dominant, which is homozygous dominant, and it has to be p squared. So we'll be able to understand as we proceed. It's good to ask. He has asked because he didn't understand. But you'll understand pole pole. And if you revise, if you don't get it right, you can ask your neighbor who understands before we can do the cut. But you can still ask on the chat, I'll be able to answer. So in the meantime, let's go to question 5. Yeah, Phoebe is explaining. Correct. Very right. And then, Phoebe, can you put the genotypic frequencies as the law of Hardy-Weinberg says? That is the equation for the allele frequencies. Put it there for the genotypic frequencies. Maybe Obize can recall. Huh? So in humans, as Phoebe puts there, the rhesus factor, genetic information, is inherited from our parents, but it is inherited independently of the ABO blood group system. You know, the ABO blood group is a multi-allelic. The rhesus factor in this case, it is expressed much as biallelic, where they are saying in humans, the RH plus individuals. Yeah. So those are the genotypic frequencies, and they should add to 1. P squared, 2pq, q squared. Just as you can see P plus Q is equals to 1, P squared 2pq plus Q squared, just as Phoebe put it there, should also add to 1. Those are genotypic frequencies. Obize, it's you we are trying to answer. I'm still reading. The RH plus individuals have the R capital H antigen on their blood cells, while the RH minus individuals do not have that. There are 2 different alleles for the RH factor, which is known as the RH plus and small r and small h. So you will assume that the gene RH, meaning that is the RH plus, produces the RH plus phenotype. And then the recessive RH lowercase will come with the RH negative. In a population, all those were stories about RH plus and RH negative. The question is here. In a population that is in Hadway by equilibrium, 120 out of the 500 individuals are RH minus. Obize is okay now. Good. We are moving together. Thank you, Phoebe, for such explanation. Obize is now fine. Question 5, the question comes here, where I need now to write it on the board. In a population that is in Hadway by equilibrium, if 120 out of 500 are RH minus, they said the RH minus is the same as R small, H small. It means those are the recessive, those are the Q squared. RH plus or R capital H, they are the rhesus positive. So we are interested in the Q squared. The RH positive are the P. The Q squared are the RH negative, which we are told are 120 over what? Over 500. Tell me if you can't calculate now. You do RH minus, you'll do, what you'll do is simple. You'll say RH negative, which is the same as RH small, they are the Q squared. So you'll do Q squared, which is 120 over what? Over 500. So it means your Q will be what? For the ones who are calculating, kindly, we can do square root. We can do square root. For us to stay active, we can do square root. And you tell me the Q. We are looking for the Q. They are the rhesus factor negative. Good. 0.489. Thank you. It means P is 0.115. 0.51. 490. Is it 490? 511. Can we work with 490 or we work with 489, though they are not far? Yeah. So meaning, let's do 0.49, 0.51, right? Then we can be on same ground, huh? You get? Because the other one will remain 0. Is it fine? The way I put it? Or 0.49, 0.51, correct. That's fine. Thank you. That is fine. So let's go to the question. It says what? Assume that the dominant, okay. Calculate the frequencies for both alleles. They're talking only about the allele frequencies. We already have the P and we already have the Q. That's fine. Do 0.49, 0.451. But remember, the 5 marks starts from up there. You tell me Q squared, 120 over 500. How you get your Q? You have to do the square root. You have to do Q 0.49. And then the part which I've left there, you'll say P equals to 1 minus 0.49. Then you'll have 0.51. For you to get the 5 marks, you need to go through all those steps for us to get 5 marks. Because somebody might ask, but that's your thing. Is it worth 5 marks? Yes, it is worth 5 marks. Question number 6. And that is the one I'll do, and thalassemia. I'll skip number 7 because it looks the same as the one we had up there. Question number 6 says, so in this case, P stands for RH plus, correct? And we are interested in RH minus. P stands for RH plus. That is right, Wendy? Yes. Keep says yes. Question number 6. There are 100 students in class. 96 did well. We are not interested in the people who have passed. We'll tell them congratulations, and they go. They enjoy their day. They have their party. But we have to concentrate on the ones who have failed and try to follow up. Why did they fail? We are concerned of the ones who have failed. Yeah. So there are 100 students in a class. 96 did well in the course, whereas 4 blew it totally and received a grade of F. Redeeming F is difficult, but you can still redeem. Then they say sorry. In the highly unlikely events that these traits are genetic rather than environmental, if these traits involve dominant and recessive allele. So they're saying, sometimes we might talk about some of the traits being genetic, but there are also some environmental factors which are contributing. Environmental factors can be different. Just the same way as all students in Kenya do KCSE, KCPE. But a student in Turkana who goes through all those difficulties, this county is where the children are learning under a tree, You can't compare such a student with the one who has everything in Nairobi. So environmental conditions can also contribute to somebody failing. But still, in Nairobi, they have everything, but a student still gets an F. They talk about if it's genetic. They have good equipment, they have everything, they have electricity, they have desks, they have books, which are provided free by the government. They're in Nairobi County. If somebody still gets an F. So they're saying if those in Nairobi who still fail, it's genetic, maybe it goes along the line, family line. That is what they're saying. Then, in the highly unlikely event that these traits are genetic rather than environmental, if these traits involve dominant and recessive alleles, and if the 4% represent the frequency of homozygous recessive condition, calculate the frequency of the recessive and dominant allele and the number of heterozygous individuals. You are told in this class or in this course which the students are taking, Q squared, the 4% who failed. We want Q, so we have to get the square root of 0.04. it means Q will be, is it 0.2? And then P will be 0.8. I'm waiting for your confirmation. 0.2. Then we can proceed with the question. Can you get for me the square root of 0.04? Or somebody said yes. Yeah. So they want frequency of recessive and dominant allele. That one we already got. The dominant allele is 0.8. The recessive is 0.2. Somebody said yeah. Oh, even Natasha said yes. Oh, thank you. Steve said 0.2. Sorry. So we are talking about calculate also the heterozygous individuals. You know, the heterozygous we have to calculate because there are traces of the people who failed in them. We want to know in this population. You know, the heterozygous are the ones which were in between there. They were in between. Just a minute. This is my screen. Is a bit. I'm just going to minimize zygous. So we are going to have 0.32. Can we multiply that one? Can we multiply? And then we do times 100 because there are 100 students. So this is already 2 times 0.16. You will do 0.32, meaning 32 students are heterozygous, right? Good, thank you. Dirango, Dodia, thank you so much. Yeah, Vitari, thank you. Oh, the other one is like the whole keyboard has been typed there, so I don't know how to refer to him. A, B, C, D, E, F, G, H, O, P, Q, R, S, T, 872. And then you put a stop with 872. Yeah, that is the answer. 32 students are heterozygous. They're in between the pass, the fail, you get? Yeah. So we are not going to do 7. 7, we can do it on our own. It's still testing the PTC, but now the number is different. You do 65, over 215. You don't do the 150. Can you do the thalassemia? I'm looking at, oh no, I have to do number 8 and number 9. They look different. Thalassemia, we saw the thalassemias, they fall under the autosomal recessive disorders, a disease characterized by the reduced absence of globin chain. I think there is a group which I gave thalassemia to work on as a group. Is a disease, thalassemia, characterized by reduced absence of globin chain, a recessive disorder present in one in 500 individuals if the population is assumed to be in Hardy-Weinberg. So we have to assume that there is none of those forces taking toll in our population. The forces are the random mating, we saw them, no mutation, no selection. That song you sing until you reach the point number 7 of these evolutionary forces. So we have to assume that they are in Hardy-Weinberg. So they're saying 1 out of 500 suffer thalassemia. Can you do the same and get for me Q? We need the square root. We haven't yet calculated. We are going to calculate in chi-squared, and that's where we are going to end. Can we get, you divide 1 over 500 and you get the square root? Somebody? Nadia, is it the 0.045? Do you people agree? Natasha says 0.002. No, that is after dividing. Do the square root. Somebody says 0. Please don't say 0. We won't get anything. Solange is which one? Oh, good. Sharon agrees with Nadia. 0.045. 0.045. It means P is equal to 0.955. We already got P. Oh, Mohammed said 0. No, Mohammed, take the 7 and it cancels. Please, yes, do 0.045. That is fine. That is fine. We agree on that, Innocent. Do 0.045. It's still okay. We can work with that. 3 decimal is fine. 2 is still okay. So the question says what? If the population, okay, the questions are up here. What are the frequencies of the two alleles? Allele frequency Q 0.045, P 0.955. Calculate the percentage of heterozygous in the population. Percentage of heterozygous in the population. Can we do that one? And then we can multiply by 100. Let me just do times 100 so that we can know. Percentage. That is the next question. Calculate the percentage of heterozygous. 85.4%. I hope you agree with Natasha. That is heterozygous. Heterozygous is always 2pq. But now they want percentage times 100. Natasha has given us 85.4, sorry. Another question, question number 9. Do we agree? Okay, we are at question number 9. So it means heterozygous, when you're asked about the heterozygous, it has sunk. So it is you to tell whether here we need square root, here we don't need square root, here we need this, here we need that. And you know, when we reach inbreeding, Nadia is talking about 8.595. That one after percentage. How will it be 8.95%? Are we agreeing? Without the 100, because if you talk about 8.595 and I do 2 steps ahead because it's 100, it will bring 859, or what am I not getting? Is it 8.5%? Nadia is correct. Alicia says Nadia is correct. A, B, C, D, E, F, G, H say yes. Sharon says yes. Madam, could you do question 7? Question 7. 1 and 3, please. No problem. I'm going to do it, but I want us to agree here. Harold, what do you say about this one which is on the board? Nadia gave me 85.4. And some people are coming with 8.5%. Phoebe says that. Okay, let's do this. If you multiply 2 times 0.955 times 0.045, who is correct? She is correct. We have Phoebe, who is also a she. Nadia, also as a she. Obiza is asking what's happening. Steve says Nadia is correct. Steve, Nadia gave us 85.4. I want us to settle this once and for all. Can somebody Yes. Everyone agrees Nadia is right. Harold is saying 8.5. Now, Obize will wait a bit because he himself is asking what's happening. We don't know which world he is in. But can we agree without multiplying by 100? Can we multiply 2 times 0.955 times 0.0.045? Oh, Nadia is saying, oh, Nadia gave 8.595. Okay, then I'm going to rectify. 8.595. Is it correct? 8 point? Okay. Huh? Oh, good. Thank you. Thank you, Nadia. Sharon Dirango has, yeah. Now we agree. Thank you so much. Now somebody is requesting, and we all have to agree because I said we have to move to the same direction. Harold requests us to do number 7, and we are going to do number 7 in totality from question 1, from Roman 1 to Roman 3. Harold, this one is for you. Yes, so that one you've agreed. It's right. It is 8.595. I think I'm the one who wrote it wrongly. So we are working on question 7. Harold requested the dominant ability to test PTC. We are still on PTC. I told you it's the chemical which is always tested in the lab when you do the practicals in genetics. Is due to allele T, capital. The ability to test, capital T for testing the PTC. Among a sample of 250 individuals, there are 215 in that population. 150 could detect the test. We are not interested in P. 150 could test. 65 could not. $65 could not. Q squared 65 over 215. I need Q where you need to give me the square root of 615 over. So can you give us, Harold? We are there. 65 over 215. Harold requested. I wanted to escape this one because it looks similar with the other two. But it's not always good to assume. It is good to ask. So can somebody give us square root? We first divide 65 over 215. Then we get the square root the way we do. Good. Sharon says 0.302. Oh, I think after we got square root, now it matches with Natasha. 0.55 can be good. We can work with 0.55. Thank you. Everyone agrees on that. 0.55. It means P is 0.45. We might want 2PQ. Let's just multiply first. We see what we are getting. 2PQ, that is heterozygous. Get us the 2PQ. Can somebody calculate 2PQ? We have P, we have Q, we want heterozygous. And that's how the population is asking. The number of people in this population who are normal, not carriers, good. 2PQ. Is it 0.4948? Thank you. 2PQ. Let me do it here. 0.495. They want percentage. So heterozygous will be what? 49.12. 49.5%, which will be equivalent to 50. Just do 49.5% the way it shows there. Don't try to round off. So we are answering, Harold, we've answered question number 7, Roman 1. Allele frequencies, you've seen T. Capital T is what? Is the P, 0.45. Small t is the Q, 0.55. Percentage of heterozygous, we have 49.5. Just write the way it is. Don't round it off, the way it's showing there. The number of people in this population who are normal, not carriers, who are normal, not carriers. Do you know why they are trying to talk much about who are not carriers? Because the law of dominance says the carriers will assume as if they are normal. The dominant allele T for testing will suppress the small allele, small t, for not testing. So if they don't specify carriers, then somebody can be confused and include all the carriers. You know, the law of dominance, when you look at the autosomal recessive dominant disorders, for the ones who are heterozygous, they show they are affected. Yes. So in that case, we are talking about P, purely P squared. Can we do P squared? Where we get 0.45 times 0.45, meaning then we multiply by the total number of people in the population, who are 215. We are trying to look at the people who are normal. They don't have traces of the allele of not testing. That is Roman 3. Number of people. Can we proceed? Do P squared times 215. Oh, 44. Good. Thank you so much. Harold, are you satisfied? Percentage is different from the number of people. Phoebe also agrees. Talha says 43.5. Of course, human beings cannot be in the form of points, so we just round it off to the nearest whole number. And that's why we are at 44. Yeah? Good. Thyroid is fine. Question number 9. I think this one you can also just do on your own, because it talks about a very large population of randomly mating laboratory mice. Contains 40% white mice. The white mice is the Q squared. What if it were 43? If it were 43.2, do 43. Human beings cannot be in form of decimals. No, dear, if it was 43.2, leave it at 43. That's how it goes. Yes. You'll just do 43. Because they are human beings. We can't put them to half. They went the other half up, and they have to be whole numbers. What are the frequencies? Oh no, what am I reading now? White color is caused by double recessive genotype AA. It means it tells you that the Q squared is 40 over 100. So that is very easy. Just get the P, and then you get the genotypic frequencies. They want you to get Q squared, P squared, 2PQ. I'm talking about question number 9. It's just the same procedure. Can we move to multi-allelic? Multi-allelic, if you read the tone of one example, the other two will be very easy. So I want us to choose of the 3 questions, 10, 11, and 12. We can choose one. Goni, your question doesn't apply here, kindly. I don't answer questions of results getting out here, and you know I'm having a class. You know that is a wrong platform where you're asking that question. You can't come and ask me when the results of ABCHB are out here, surely. And you expect me to answer. I think you should respect the platform, because it's not for that. We are going to vote. They're saying we already have 2 for 11. 10 is 1. I want us to have one which will apply to the other ones because it will be the same. No one is touching 12. 11. No, but Toa, so Katoa. Are you saying Katuas? So Katuas as Nini twice. So nam count moja. One, even Eddie. Eddie Kimanzi has come twice. Kimani, you've come twice. Steve, Eddie, Sokatua. Oh. But Natasha is the only one saying 10. Natasha, see how watu wamekuovertake, so we'll go with 11. Natasha, why do you want 10? Maybe there is something which you want to tell us, which we don't know. We go with majority. Natasha, I want you to agree with us. We are going with question 11. I hope you are fine because the same formula will apply to the other ones. Huh? For this multiallelic, I advise the students to always draw the Punnett square so that you can know, for it to guide you, which of the genotypes are we talking about. You get? Not that I give marks for this Punnett square, I don't. But you will know it is ABO blood group system, where A stands for P, B stands for Q, O stands for R. A, P, B, Q, C, R. Meaning, where you get AA, you will have P squared. Where you get AB, you will have PQ. Where you will get AO, you will have PR. Good. It directs you, and you know the genotypes that you expect, you know the allele frequencies, so it's easy. Then BA, you will get QP. BB, you will get Q squared. BO, you will get QR. Then you come here, OA, RP. OB, RQ. Then OO, R squared. So it means we have alleles P plus Q plus R equals to 1. But then we have the genotypic frequencies where we start with P squared there. You have 2 of PQs. You have Q squared here. You have 2QR. You have R squared 2 plus 2PR, all should be equals to 1 as the alleles frequencies are. So it helps us to know which of these genotypes we are working with, which of these allele frequencies we are working with, but still the allele and genotypic frequencies should add to 1. 12 and 10 is the same, so it's just a bit tricky. That's why I was saying 10. 12 and 10. Sorry. 12 and 10. Do they talk about A blood group and B? A blood group and B. It's not tricky, my dear. Not tricky at all, at all, at all. Not tricky at all. Don't worry about trickiness. I'll explain to you. Now, question number 11. What you have to know in the multiallelic, you have to be given the genotypic frequencies of any 2. It can't be 1. Of any 2. Then you are going to find that one which is remaining. But then A has to go with P in ABO blood group system. Q has to go with B. O has to go with R. You find when this question sometimes is asked to the students, somebody just decides to interchange. Now we can give R to what Q has and let Q is the one to remain unknown. Who told you that you should always just try to confuse the examiner and the examinee and everyone? Do it the way it is asked. If P stands for A, give P the A. Q stands for B, give B the Q. R remains with its O. Hii maneno unachanganyisha kila mtu. Una calculate values, they are right, but now zimegeukwa yenye hata ya 2PQ imeendea 2QR. No. Delphine says yes, please. What are we yesing about? Delphine, we need to know why you are yesing. Why are you yesing? Are we on the right track? Okay, let's go to the question. As Delphine says yes, I need her to clarify why we are yesing. But our question number 11 says, Natasha, I'm going to explain to you number 10 and 12. Let's work with this 11, then I'll explain to you question 10 and 12. In a multi-allelic blood group, you can draw if you draw the Punnett square like that, you will know the allele frequencies, you will know the genotypic frequencies. Look at this. There are 3 alleles. So in this case, we have the 6 genotypes. So we are saying in an ABO blood group system, 1,200 individuals were sequenced. It means N equals to 1,200. You have to put the total number and you'll know that N equals to that. So after knowing that, then the next thing is you are talking about, let me see the question. 400 were BB. If you look at BB there, is it not Q squared? 400 were BB. You come here and say Q squared equals to 400 over 1,200. We want Q. So if we want Q, do square root of whatever you have here, as we always do. Then inasema gani tena? 100 wa OO. OO is R squared. Do square root 100 over 1,200. So R equals to what? Can somebody give us square root? That is the up one. There is 400. It doesn't look clear. We don't have P. We are going to look at P. We want Q and we want R. Can you do the square root? Oh, R, good. Natasha, is that one square root? Soccer too. 0.577 for who? We have Q and R, kindly. And Natasha, tell me if the R is the square root. Q, good. 0.58. It means the R is that one. The one which Natasha gives, 0.28. Can we do 0.29? Because we already have this one. 0.29. Thank you. Very simple. You know what some students do? Which destroys, sorry, which destroys everything? After we have been given Q squared as 400, R as 100, do you know what some students do? They get the total and they minus from 1,200. It doesn't make sense. You are going to get lost as you go. Go this way and you get everything smooth. What we need is, for us to get P, you do Q plus R, 1 minus what? 1 minus Q plus R. So P equals 1 minus That is 0.8 what? 87. Meaning P is 0.13. Is it right? Yes. Now, we are going to start calculating. Those are the allele frequencies. We want genotypic frequencies. Kindly do P squared, somebody do Q squared, somebody do R squared, somebody do 2PQ, somebody do 2QR, and the last person do 2PR. We are going to look at the genotypic frequency. The first person, P squared, we clearly have Q. I'll underline the allele frequency. We already have Q, we have P, we have R. The ones which are underlined are the allele frequencies. Can we do P squared, Q squared, R squared, 2PQ, 2QR, 2PR? And then it has to add to 1. Let's continue. 0.01. Thank you. 0169. Let's proceed. 0169. Next one, Q squared. Thank you. 0.336. 0.336. Next one. Yeah, 0.0169. That one is written. Thank you, Lorna. Yeah. Which one is that one? R squared, correct. 0.0841. 0841. I assume this one there is a 0. 0.0841. Talha, thank you. Lona, thank you. A, B, C, D, E, F, also the same value. Thank you. Yeah, we are at 2PQ. Remember to multiply by 2. All these should add to 1. Genotypic and allele frequencies should add to 1. We are at 2PQ. Yeah, somebody already, ABCD, 0.1508. 1508. Let's proceed. 0.1508, correct. I just write it the way you give it to me. Yeah, Phoebe has confirmed, Talha has confirmed. So that's correct. We can go to the next 2QR. 2QR. 0.3364. 0.3364. 2PR. Correct, Harold, that's fine. Stanley, that's okay. Thank you. It's the same answer. The last one, 2PR. 2PR. 0. Is it the same as 2PQ? That one I have to put a pause. A, B, C, D, E, F, G, H, Q. The 2PQ was 0.1508. Do someone agree again? 2PR is 0.1508. The same value? No. Phoebe disagrees. Okay, we have to write this one. 0.0754. 0.0754. I'm going to add 10, 18, 18 what? I'm just going to add the values which you are giving me. 18, 22, 26. Let's see. Carry 2. 8, 14, 18. 18 what? 18, 24, 29. Carry 2. 3, 6, 14, 19, 22, 29. Carry 2. 3, 5, 6, 9. Good. We are going in the right direction. 0.99996. That's fine. I don't have any problem if you can memorize. I said the table. I don't mark the table. There is no mark for the table. Good. That is fine. That is 1. Correct. So when you're told, those are the genotypic frequencies. Sometimes you are told to calculate the expected genotypic frequencies. Don't get stressed. Expected genotypic frequencies multiply by the total number of people in that population for each of the genotypic frequencies. Are you getting it? Students, are we together? If you are told expected genotypic frequencies, multiply each of those by 1,200. And remember, they have to total to 1,200. It should not miss. Or if somebody asked the expected genotypic frequencies for specific ones, AO, BO, A squared, you should know the difference between expected genotypic frequencies and the simple genotypic frequencies. So if you ask genotypic frequencies without the word expected, don't multiply by 1,200. If you are asked including the expected, after getting the genotypic frequencies, multiply by the total number of people in the population. Natasha, I'm going to explain to you question number 10, just in words, so for you to know. So question number 10, they've already given for P, is Natasha now I'm addressing, because I asked her why did she insist on question number 10, and she said question number 10 and 12 look similar and it's confusing her. So the formula is the same, but in this case the total number of population instead of 1,200 are 800, but still even the statement is the same. A bit difference because here we have P, blood group A is given. We have P squared, which they're talking about 200 out of 800, get the square root. And then B, which is Q, 25 out of 800, get the square root. What is not given is R. Just follow the same route. Question number 12, but they look the same. It's only that the figures are the ones which are different. Question number 10 and 12, the similarity is they've given for P and Q squared, but not for R. You get? This Obize is in class or is doing another thing. We are moving, my friend. Now we are not going back. Assumptions of Hardy-Weinberg. Here we can read on our own, but I'm going to stress much on what we need to cover. You get? Question 13, I said in class last Thursday that if you are asked about small population size in Hardy-Weinberg equilibrium, talk about the two phenomena, the founder effect and the bottleneck. Describe very well the bottleneck. The population is swept. After the population is swept, it could be any of those causes. It could be disaster, it could be drought, any of that which can come, calamity which you can't avoid. Then there are a few survivors who might have a condition, and then when the population grow back again, the survivors will determine the allele and genotypic frequencies of the new population. Then, for the founder effect we mentioned, they move from the larger population, they go and settle in a small area. In that small area, inbreeding will be felt because they are going to mate among the people who are relatives. They are genetically related. I'll answer that. Just wait a little bit. I finished this one. So the people who are genetically related, they've been forced to be in a small area. So when the population grow big, if any of the founders had a condition, it will be determined by the allele frequencies and genotypic frequencies will be determined by the founders. So in the case where they talk about genetic drift, don't put big English. Go straight and give it the two phenomena: effect of small population size, bottleneck, and what? Founder effect. In the case where they talk straight about the small population size, because the Adi Weinberg assumption says the population should be large enough. But where the population is small, then the genetic drift is felt. And when genetic drift is felt, two phenomena are involved. It's either founder effect or the bottleneck. Let me come back to the question. The thing is saying, if someone asks, who is someone? If you ask me, the expected frequency, which frequency? Expected genotypic frequency. Delphine. Expected genotypic frequency. There is English you are mixing, multiplying. There are many which I don't understand. Okay. So before I say yes, I might say yes, and then you'll come and you come and penalize me. Madam, you are the one who said it when we were revising online. Let me read it again. So if someone, okay, let me assume myself. If I ask you, not someone, if I ask the expected genotypic frequency, is it the same? Huh? Daphne, don't put many things in one basket because they'll explode. If it is expected genotypic frequencies, what I want you to know here is you still have to calculate the genotypic frequencies as you know them very well. Then you total the number of people in the population. And then now you are asking that the number of individuals means the same thing. You have to multiply by the total number. Which number of individuals? If you ask the number of heterozygous in the population, yeah, it goes toward the same direction. Let's say we ask, yeah, you are making sense there. We ask, what is the genotypic frequency for the heterozygous? For example, you do 2PQ. Correct. Yes, I'm trying to make it clear. We've been asked, do the what? Get genotypic frequencies for heterozygous, correct. You do 2PQ. So it finds when you've already gotten the P and the Q, you do 2PQ. You just substitute. After the frequency, then the question asks, another section of the question asks, what are the number of individuals who are heterozygous? You are right. You multiply by the total number. Good. That's correct. Where were we? Yeah, I was explaining small population size before we can go to inbreeding. So Write short notes on selection model where both homozygous dominant and homozygous recessive are selected against. It means the system eliminates dominant, the system eliminates recessive, the system only leaves heterozygous. Now, that is the selection type of stabilizing. But the selection model, what I told you, the selection models, go straight and give me an example of a disease. In this case, sickle cell anemia, and describe the model. And I mentioned it in class, homozygous dominant, the normal HB, the falciparum will not leave it. The plasmodium will attack it very fast. So they'll die of malaria-related cases. Homozygous recessive, plasmodium will not fight for the sickle-shaped HB. So the sicklers, homozygous recessive, will die of bacterial infection-related cases. Maybe they be anemic, so they'll also die. The system, the ones which will be able to represent their genotypes in the next generation are heterozygous. They are symptomatic. You know, in the case of sickle cell anemia, the carriers are healthy. They are not affected, whatever we did. They are only affected when they are homozygous recessive. The carriers will always survive, especially in the current world where we have a lot of drugs for managing the sickle cell. You will not even tell that they are heterozygous until you do the genotyping, and you'll know that the traces of the sickle cell is there. So they're the ones who are going to survive. So you go straight and you mention the disease, and then you describe the model. And remember, we even described a model where we were talking about, is it the next one? Yeah. Number 15, a model where homozygous dominance is selectively disadvantaged. We are selecting against homozygous dominant, and that is the CCR5 gene, the one for HIV. And I said, don't try this one at home. Madam Winnie taught us, so you can have unprotected sex left, right, center, and then you think you're not going to be infected. I didn't say that. I was giving an example. This was done in Europe, and they found that the people who do not have the traces of CCR5, that is the homozygous dominant, died of HIV-related cases. The ones who are heterozygous, meaning they have the CCR5 and also the dominant allele for healthiness, they have partial immunity. The ones who are fully protected are the homozygous recessive. They have both mutant, this CCR5 gene, 32 base pair mutant gene. So that point, you are talking about a selection model where the homozygous dominant is selected against, while heterozygous and homozygous recessive are selected for. So that one you can read and understand. And even non-random mating, you can discuss the associative mating, the positive, the negative, their effect on allele and genotypic frequencies. You can talk about inbreeding and outbreeding, their effect on allele and genotypic frequencies. So the Hardy-Weinberg assumptions we can read on our own and understand. I'm going to do inbreeding, one of them, which you have to choose for me, whether 17 or 18. We can't do all, just by example, the way we did multiallelic, because we're already at 1 hour. We are almost going to 2 hours. I don't always like to overstay with the students, because now the concentration level is going down. So I'm going to use one to represent the two questions. Then I'm going to use 1 to represent the 4 questions in chi-square fitness test. Which one do we choose? We are at inbreeding coefficient 17. Can we go with what Sokatua says? Sokatua says question number 17. Remember, inbreeding comes handy when we want to detect if the population is in Hardy-Weinberg. It comes as a result of, don't you like Sekatua's idea? This time we like go with, I'll go with minority, because the other time I was unfair for Natasha. And tell her, you will tell me why you want number 18, not 17, which has been mentioned by Sokatua. And this one is also Alleluia, innocent. Or Alleluia, innocent. Why do you want number 18? Can we agree we do number 17? Nadia says 17. Sokatua started with 17. There are no difference between these two. One will lead to the other. You'll understand the other one if you show. So we'll go with 17. That's what I think this time. Yeah. Let's just work with 17. Because I think Sokatua was the first one to comment. The other one, Natasha, was the first one to comment. And the wave didn't go her side. So, yeah. I think they came and agreed. Innocent agreed, so it's fine. Yeah, even Sokatua agreed. So let's work with 17. We said inbreeding will come at the point where we are trying to test if there is non-random mating. And we said inbreeding sometimes come as a result of some cultural practices or even the genetic drift where this population has gone to settle in a small area, or they've been swept out and a small population is remaining, so they have to mate. So it leads to mating of the people who are genetically related. And inbreeding brings much of homozygosity. So if you see a population inbred, that population has homozygous, no heterozygous there. So we said that for us to calculate the inbreeding, we have the inbreed coefficient, and you talk about observed over expected. So what you do first you have to get the inbreeding coefficient. If the formula is wrong, let me know, but it's observed over expected, I think. And then you minus 1. So you have the inbreeding coefficient. If it is greater than 0.5, then the population is homozygous. The population is inbred. If it is less than 0.5, the population is not inbred. It means the population follows the Hardy-Weinberg equilibrium. If the population is more than 0.5, reject the null hypothesis. The population is inbred, is not in Hardy-Weinberg equilibrium. So, given the following data, we are going to calculate. We are at number 17. Homozygous dominance, 135 over, I think the total is 200. Yeah. We are going to calculate, all of us. Heterozygous, 40 over 200. Homozygous recessive, 25 over 200. We can get the genotypic frequencies for each of those so that we can get the allele frequencies. Someone? We are not square rooting. Here, we are not square rooting anything. We can get the genotypic frequencies first. So this is what I was saying. This is up bottom. The other one for heterozygous was bottom up. We always start, many cases we start with getting the genotypic frequencies which lead us to allele frequencies. But in this case, in the other cases, we were starting with the allele frequencies which could lead us to genotypic frequencies. So here you start with the good genotypic frequencies. AA 0.675, AB 0.2, BB 0.125. Can this person give me complete? This person of 40? Why are they not adding to 1? Are they adding to 1? 10, 9, 10. Something is wrong. Is BB 0.125? AB is purely 0.2. Can you recheck BB? Are they adding to 10? Oh, yeah, correct. They're adding, sorry. They're adding, correct. They're adding. Sorry for that. We are going to get A, which is also P, the dominant allele, Q, which is also B. So what we always do in a longer way, 0.675. And then we get half of this, which is 0.1. Then Q, you are going to do 0.125 plus 0.1. So P is 0.775. I think you agree with me. Q is 0.225. Is it correct? Correct. Now, we need to get expected because observed, tuko na this one. Si tuko na 40. Observed is 40. In fact, it is observed heterozygous. I should specify. Over expected heterozygous. We are going to have expected by doing what? 2 times 0.775 times 0.225 times what? The total number of people in the population? 200. Can somebody do that calculation? Let's multiply. We are looking at expected. I should name it. Expected. We are calculating expected heterozygous. Expected heterozygous. 69.75. Thank you. Now, back to our formula up here. I'm just going to substitute. Let me just rub it a little bit so that we can see whatever is up here. So you do, observed is 40. Can we first divide 40? The easiest way is divide 40 by 69.75. Just divide 40 by 69.75, and then we can find the value. That's what we subtract from 1. That is the easiest way. We've gone up from wherever we were, down there. Or the students can still see. I think that is still visible. 1 minus 40 over 69.75 equals to 0. You've subtracted? Have we subtracted? So Katua says, if you divide, you get 0.5734. Then Harold says the final, okay, good. So we go with the final. I don't know why this my thing want to fall. Just a minute. So we go with the final of 0.427. Is it? F 0.427. So you say the population not in bread, right? Not in bread, not in bread. So you do what? You accept what? The null hypothesis, because the null hypothesis says the population is in Hardy-Weber equilibrium, no inbreeding. You can see the value is 0.427. So it is less than 0.5. So the population is not inbred. It means you accept the null hypothesis that the population is in Hardy-Weber equilibrium. I'm also now exhausted. That one applies to question number 18. I want to do chi-square test, one of it. So you can decide, because chi-squared is a bit intensive. We are going to calculate expected for all the genotypic frequencies, then we can go. Please don't get tired. We are at the last one. Just choose one. I need to see 22. 22 1. So Katua says 22. Another person, if you don't say, then I'll go with Sokatua's. We are at chi-squared fitness tests. Can I pick the one for Sokatua? Then we can finish the night. And then I can leave you people to go. So the reason why we are revising all this, some students confuse the inbreeding. Where does that 0.1 comes from? Which 0.1? And I've wrapped the board. Can somebody answer Solange? Which 0.1, by the way? Where did you get 0.1? Did we get 0.1 anywhere? Okay. We are going with question number 22. Nadia says 21. But now 22 has 3 people. Obize says so. Ntwari says 22. Nadia, I like when good. Somebody has answered, Solange. And we said, yeah, we said that the heterozygous have traces of the dominant allele and the recessive allele. So for you to get the allele frequencies, you have to divide by half, because each one of them has a share there. You get good. I don't know. Nadia, I don't know how you will feel, but I can see 22, 3 people have number 22. But let's get it going. So 22 talks about the friendliness of a cat. They say, remember, the essence of chi-squared fitness test is to see if there is any assumptions of Hardy-Weber which the population is going against. You get. So the chi-squared fitness test is the one to prove that our population has perturbations or not. are there some forces which are going to shift our allele and genotypic frequencies. And if you talk about the genotypic frequencies, we talk about the ratio of 1 to 2 to 1, where the ratio 1 stands for homozygous dominant, 2 stands for heterozygous, and 1 stands for homozygous recessive. If there is any force in them, then you'll find that the ratio is no longer 1 to 1, but it has now increased, something like that. So, the chi-square fitness test, the formula says observed minus expected squared over expected for all the genotypes. By writing that formula there, we are set. We start from wherever we started, the way we were looking at inbreeding. So some students will confuse this formula with the inbreeding one. And then you find in inbreeding somebody looking for all the genotypes, observed, expected, squared, over expected. Until you ask, where are these people now coming from? Where were they when we were revising? And that's why revision always very important. You will not forget what we revised. We are talking about in cats, friendliness is determined by dominant gene F. The recessive genotype produces an unfriendly cat. The small f will bring an unfriendly cat. The capital F will bring a friendly cat. So the genotypes of several cats are determined to be 40FF. You know, my phone is almost going off. I didn't charge it well, but I hope it will be able to take us through. I don't know whether it has to go at 15, but it always does go off, even if it's 2%. What I want to see is if my students can get this point. I hope it's visible. It has started to become a bit dim. FF is 34. Out of, we have what? No, 40, sorry. 40. Out of, we have 65 or 75. Yeah, that is 75. F, small f, 34. Then small f, 1 out of 75. Can you find the genotypes? You can just try to do a bit faster so that it doesn't go off. Homozygous dominant, homozygous recessive, heterozygous, the way we did when we were looking at the one for inbreeding. And then we can find capital F, small f. That is the next one. So can we do FF? Somebody? Somebody was already have. Thank you. It looks like heterozygous. Harold, what you've given me, I want you to show me capital F, or it's the way it is. I think that one is heterozygous, which Harold is giving. 0.533. Then Harold's one, I think, was heterozygous. He didn't make a mistake. Oh, good. Let me get the one for Harold here. 0.4533. So we can leave the other 3. Okay, that is, I've seen that. Can we go to the last one, the smaller one, homozygous recessive? And now I know they will all add to 1. Homozygous recessive, the last one, 1 over 75, 0.013, 0.013. I think it brings it to 9999, which is fine because of the points which you've left there. Now, if we settle to this, it will be 534501. Which one was more than, because the 9 will leave something out. There is a value which we've left, 0.00. So, can you do half? P is 0.55533, half of this, 0.013 plus. We can do half of the heterozygous. You give me something, you give me a value. That is why we are going to round it off. Half of 0.533, half. Zero point 267. Let's work with 0.267. 0.267, so that we can recover the other one. Let me see. Now, can we have our P if we add? Two. Did I write it well? 2, 2. Oh no, wait. No, dear. Yeah, wait. 2, 2. We do 2, 2. 227, right? Agreed? No, dear? I think you mistaken something else there. Can we do 227? We add? Oh, good. P is 0.76. So let's go straight and give Q 0.24. Perfect. Now, we are going to get expected. Let me write the P and Q so that we can wrap this. Then we have space for. So P 0.76, Q 0.24. Allow me to rub where we've gotten the genotypes so that we can have space for expected what? Expected genotypic frequencies. I have observed, I'll be able to read. Can we now calculate the expected? We are calculating expected genotypic what? Frequency. That is not girlfriend. Genotypic frequencies, GF, not girlfriend. And then you start getting confused here. No. So P squared times 65, Q squared times 65, 2PQ times 65. Can we do that? I've put there up. P is 0.76, remember? Do 0.76 squared times the total number of people in population. Okay, P, good. Natasha has done everything. 42.49. 42.19, sorry. Q, 4.32. 2PQ, 27. Do you agree? Somebody says I didn't write it well. Was it 75 or 65? Let me go back. 75. Is that one what we worked with to get the genotypic frequencies? Did we do 75? Okay. Somebody will say, Madam, you are the one who wrote that one. So it brings it right. They'll still add to 75, right? Good. So we have expected. Now, let's go to the chi-squared. Each one of them do this. We start with homozygous. We have observed minus expected squared over expected plus heterozygous. We had what? Which one was that? Am I 34 observed, expected, squared over expected plus homozygous recessive, observed minus expected squared over expected. Remember, at 2 alleles biallelic, degree of freedom of 1, we have a constant value, 3.84. If this value is greater than, the value which you get is greater than 3.84. What am I saying? If the value is greater than 3.84, then the population not in Hardy-Weinberg. But if the value is less, greater than, population not in Weinberg, less, population in Hardy-Weinberg. So here you accept null hypothesis, here you reject null hypothesis. So, good. Will you be able to do that? And you give me the total, what you get? Yeah, 4.48. So, p squared is even going lower and lower, 0.114. Q whichever keeps the pace there is 2pq. 2pq is 2. Q is 2.55, which already beyond. So it means in this case, we are seeing more of selection coming in. And it looks more like stabilizing selection type, because the heterozygous are retained. You can see the homozygous dominant is depleted, it's getting selected against. But now the Q squared are also increasing. So there is a selection working on the population. So it helps us to know. So at that case, you're going to reject the null hypothesis. Before you reject the null hypothesis, you have to tell me whether the population is in equilibrium or not. Before you talk about rejecting or accepting the null hypothesis is inbreeding, you have to tell me whether the population is inbred or not. That is in inbreeding. In chi-square test, before you reject the null hypothesis, you have to tell me first, the population is in Hardy-Weinberg equilibrium or not. That's how simple it is. It's going to apply to all this. In that section of chi-square test, that is what you do. Yeah? Thank you so much for your time. And I wanted to ask, do you have a cut at 10? Do you still have a class at 10? Because I need to pick my children's, my daughter's report book on that Thursday. Though I already told the teacher, I'll go to work first, then I come back. If this pathology teacher or are you fine with Wednesday? Do you still want to do it on Thursday, the same time as we have? Is the pathology teacher there? Because we don't want to play around with people's time. I don't like always taking somebody's time. So maybe we can just retain it at that time in the morning. If we do it in the morning, early in the morning, even by 8 we can do it at as early as 8. Oh, she's not there. Is a she? Yeah. Oh, so the class which comes after our class, the teacher is not there. So can we agree? We have the cut at 11? Or renal physiology? I don't want to use somebody's time. If you're sure he's not there, then we can have the cut at 11. I rush in the morning, I pick my daughter's report books. I always have to be there. Good. Steve has agreed. Oh, you have another cut at 1 p.m. Nadia, are you agreeing with what Steve is saying? Can we have it at 11? 11 is fine with me. That will accommodate my time. I rush for the report books, so I have to be there in the morning. I just tell the teachers I'll be there early, and then I pick. Then I can go. Or Wednesday. Do they agree with Wednesday? Wednesday at 10 is fine. Do they agree? Steve, can you say something? We can just start at 10 a.m. Nadia is saying, or Wednesday. Are some people fine with Wednesday? We have a class on Wednesday at 10 a.m. Then that is not working. I like when people agree. Coach. Then let's do this. Let us settle with our time. No, Thursday 10 will be tricky for me because I can't go there and get the report books by 9. That one I'll be lying. If I get by 9 from Nairobi to Thika, I always count an hour, and sometimes they delay. Wednesday 2 p.m. No, Thursday 10 or 11. That's a bit tricky for these students who are starting class at 1. Okay, let us do this. Let's settle with 8. Thursday 8, I'll be there. So that I finish early, then I can go for the report books. Thursday at 10. Thursday 10 will be tricky, Cindy. That is what I'm trying to say. Look at Harold is saying tomorrow. How can you do it tomorrow now? Be fair. People need to catch up with whatever we've discussed. Ahmed is just saying fine. He doesn't know which one is fine. I want us to agree. Sakatoa is bringing it even further. 7 a.m. Kama lectures data sifikangi 7. Let's do Thursday 8. Correct. So, Steve, Thursday 8 is fine. Cindy, Thursday 8 will be fine. I'll rush and come for the cut, just 1 hour. Then I go back. So remember, carry your own calculator so that you don't disturb anybody's peace. Madam, can that person... There was a guy who was always asking for pencil. I don't know pen. Don't do that again. If you start disturbing the peace of another people who already started with their calculator, that Ahmed who was sitting at the wall, ni kama anataka kuitasha pen, anataka ruler, don't disturb people. Come with your own calculator, kindly. Even in exam, have your own, so that you show that you are prepared and you can, you get. So all the best. It's set. So Thursday at 8 will be fine. Then I can come back and rush and get the report books. It's okay. Thank you so much. Yeah, thank you so much. I'm going to be fine. Yeah, I'm just going to get hot water and some ginger. Today is even better. I can talk. Thank you so much, everyone. Thank you for your concern, and may God bless. Let's keep on revising. When are we having our exam? I checked the timetable, and I could see for my BMLS upgrading. I didn't see for my Bpharm students. Steve, can you tell me? Can you tell me when? Tell me. 7th August. Huh? That is Friday. But the Friday is always for the what? For the weekend. Kumbe, you also start early. Then early the better. That is fine. I didn't even know. You see, if I would have not communicated, ningezubaa tu ningoje tarehe, because the other one is done on Monday. So that is good with me. I can go for early holiday. If I do the one on 7, the other one on 10, then I can mark and go for a bit of holiday for 1 week. That is fine. So they should not even, yeah, the earlier the better. I know the students are prepared. And 7th is a graduation. No, don't get disturbed. Don't get distracted. You are still preparing your path. Let the other ones enjoy as they fly their hearts high. Yeah? So we'll just stay focused. We'll assume that we can concentrate. Let's just stay focused. Yeah, that's fine. Have a good night, everyone. And thank you for your time. May God bless as you prepare for the CAT and the main exam. Thank you.